Good morning, everyone. First of all, I really just want to thank the organisers for inviting me here. It is an absolute pleasure. I'd also like to slightly apologise because I got up this morning and it was raining and I thought, great, England came with me. I'm going to say I'm probably not going to answer this question during the talk. It's one of those where you put up the question because you think that will make everyone come. But the reality is predicting the future in that way is not something I'm going to go for. But what I'm going to try and do is give you a feeling of where we are up to in attempting to do these kind of problems and the steps and things that we need to think about so that we can really get to the stage that you could just design an antibody therapeutic on a computer. So first, even though we've had the COVID pandemic, so when I say the word antibody, I no longer have a face full of everyone's blank faces staring at me going, I still feel I probably think about them quite a lot more than everyone else in the room. So I'm going to do a little bit of a primer to begin with. So antibodies are natural proteins in your system. There's the kind of pretty picture of them on the right-hand side there. So the blue and pink bits, that's the antibody, grey bit, the antigen. They're quite big if you're thinking about them as a therapeutic. There are around 10 to the 11 distinct different antibodies floating around in your system right now. And they are one of your primary lines of defense that is basically keeping you alive and stopping you feel sick. The theoretical antibody repertoire, so the number of different ones that could be made, it's slightly hard to estimate, but it's somewhere between 10 to the 13 and 10 to the 18. So they have huge diversity possible. They're really good at binding to things. They're really good at binding with high affinity and very specifically. And obviously, that makes them a great idea for a drug. They're the fastest growing class of drugs, and they are the most valuable class of drugs. If I go into them in a little more detail here, you can see the kind of antibody-specific sort of terminology I'm going to talk about through the talk. So schematic on the left-hand side, that's a kind of full human antibody. And the kind of bits that I'm going to talk about a lot are what are called the VL and VH domains, because that's where the binding occurs. So those top two domains, I'm basically not going to talk about the rest of the antibody at all. And then on there are 6 what are called CDRs, complementary determining regions. They're basically 6 loops, and those loops are the primary agents of binding to the antigen. So it is those we must engineer if we're going to get binding to what we want to bind to. And we must understand the surface of the entire antibody to understand all its properties. And then at the bottom there, because it turns out it matters a great deal, is the genetics of how an antibody is built. So you've got these 2 chains, so the sort of L chain and the H chain, light and heavy. And this is just the VH and the VL, and they're made up of a set of genes. And you have several of these. You don't have one VH gene, one VD gene, one J gene. You have lots of them, and they recombine in various ways to create the antibodies. And then after they've recombined, or during that recombination, you also get lots of somatic hypermutation. So lots of mutations occur every time an antibody is made, and that's how you generate the diversity. But if it remains just like the genetics, we'd say it was a germline antibody. So some of the antibodies floating around in your body are germline, and some of them are highly mutated. So what do we need to do if we want to make that antibody into a drug? Well, the first thing is it's got to be functional. So it actually has to have an effect on the disease you want it to have. And primarily that comes from its ability to bind to the target in a specific and sensible way. But like all drugs, that's not enough. It's also got to be safe, basically, and you've got to be able to manufacture it. So for antibodies, the kinds of things we think about there, the first one we think about is human. If I inject into you a non-human protein, I'm not proposing I actually do this, actually your own antibody system, so your natural immune system will go, oh no, and bind to it really quickly and knock it out. It could also cause an immune storm and actually make you very ill indeed. But of course it's a non-effective drug, either of those cases, because of course your own body's taken the drug out, it doesn't exist anymore. So being human is actually quite important here. And then there's this concept of what's called developability for an antibody. What that means is you need to be able to make this antibody and keep it, I always say on a jar on a shelf, but really I meant in a very specialist bottle in a fridge. But you need high enough expression. You've got to be able to actually make the stuff. You need it not to aggregate. Injecting people with aggregating proteins, once again, very bad idea. So we need to make sure it doesn't aggregate. We need it to be specific. We need to have low viscosity. So we need something that it binds, is functional, but is also behaving very well as a protein. And we need to control all those properties in order to make an antibody drug. Now into what my group actually does in the area. This slide is a very quick, and I think the list of what is, roughly speaking, still up to date out of my group in terms of the tools and databases we build in this area. You'll be really relieved I'm not going to try and talk about all of them. It would be fun, but really don't have enough time. I'm going to do a very quick spin around this slide, but there are a couple of things I want to say before I even begin that. The first one is, which, as was mentioned in the introduction, all of these tools and databases are completely freely and openly available. You want them, download them, take them, use them. Doesn't matter if you're industry or academia. And the second one is, and I think this is important because it relates to the way the field is moving, if you look at the dates on those tools, yep, most of them are incredibly recent. And that's not because, I'm desperate to have the most recent paper. It is because of the speed that the field is moving. So things that my group wrote 4 or 5 years ago quite quickly become obsolete at the moment. And that's both terrifying and very, very exciting. So very quickly around the slide, I'm actually going to start on the right-hand side of the slide with the databases. So at the top there is the observed antibody space. That is a collection of all of the publicly available antibody sequence data. Has a couple of billion antibody sequences in it. And they're all clean, sorted, numbered, annotated, so you can just take the data as it is and actually be able to use it in any way you see fit. Below that is a couple of structure databases. So SABDAB contains all of the structures of antibodies that are publicly available from the PDB. And below that, you have TheraSABDAB, which is all of the antibodies which have got what's called a WHO identification number. So they're the things that have entered phase 2 clinical trials. So we know what's happening in the drug market there. Those databases actually make me very happy because we built SABDAB, you can see it quite a time ago now, because if you type the word antibody into the PDB, the one thing you didn't get was all the antibody structures. I don't know if you've discovered this with other proteins, but you get all sorts of stuff. And now we're coming full circle, where the PDB is now using our annotation to correctly annotate all of the antibodies in the PDB. Below that, we have PLABDAB, and this is all of the antibodies that have been patented. So you can find out what's been patented in this space and compare what you're doing to what exists there. Then COVABDAB, we have a few other databases like this. These are specialist databases of all the antibodies related to a specific disease. So here, this is COVID-19, so it's all of the SARS-CoV viruses. That's exciting. I will wait. It's an emergency alert. It says so on my phone.
No problem.
No problem? I'm being told I'm not having an emergency. It's fine. Okay. So I'll just go down to the bottom. In green, I've just marked up because we also do all of this with TCRs as well. So if you're interested in T-cell receptors, the structures, the sequences, and some of the other things exist there as well. Then very quickly around the tools. At the top, I'm going to talk about this a bit more, predicting the flexibility of antibodies. Next, being able to number them, so being able to actually work out exactly what residue I'm dealing with at what time. A bit about humanization, so I mentioned that in the properties, so I'll talk a little bit more about HuMatch. Language models, because everybody loves those. An ability to generate antibodies, so just generate antibody sequences. An ability to search the databases. That sounds a really easy task. We've been able to search sequence databases for ages. Turns out, if you have 2 billion antibody sequences that are all really similar to one another, most of the standard searching tools don't work because they can't do the spreading and use the mathematical tricks of clustering to make them work well or fast. Then structure prediction, and then inverse folding, so creating the sequence that will go on a structure. And then work on predicting, so space 2 and paragraph and paratyping and baselining the buzz and DLAB, all about predicting binding. And then TAP, which I'll talk about a bit more, looking at the developability of antibodies. I decided to start talking about language models, mostly because everybody loves a language model at the moment, so everybody listens when you talk about language models. You know, you say the words ChatGPT and everyone gets excited. We built a language model for antibodies some time ago, and there's a few of those out there. People have been building these. And we built it from our OAS database, so we've got tons of sequences. I'm sure you've seen protein sequence language models like ESM. So the sequence of residues is your language, bang, in it goes. And people have used these types of language models to improve and predict antibody properties. That could be the end of the story there. Sort of a nice story. And this is just sort of an example slide to show how it works. On here, I've just got, happens to be an antibody that binds to COVID, COVOX-253, and that's its sequence across the bottom. And then underneath that is its germline. So that's what it came from, all right? Now, I'm only doing the V gene here because it's easier to look at. I haven't got the D and J on the far end. Where those are red is where the COVOX is different from the germline. So if you look at the very beginning, there's a methionine in the germline, the M, and there's a valine, the V, in the COVOX. All I've done is use a language model the way we like to use them. So I have just masked every position, one after another, and asked the language model, what goes there? Easy question. And if you look at what it does along here, you can see there are some big spikes. Yep. What those big spikes are is when I mask a position that is non-germline, so that's an important mutation because that's part of what allows it to be a special binding antibody, it goes, best prediction for that, germline. And it's sort of obvious why it would do that, because the germline's really common and everything else isn't. And this tendency towards germline, I just showed you one example, isn't special for my kind of Ablang model. Those are two other antibody models there. And then I've also got ESM2, so the sort of general protein model there, just to give a comparison. These are residues which should not be germline, and almost 100% of the time, these models will tell you, put it back to germline. So if you're trying to use this model to optimize your properties, what you're actually doing is something I could have done without wasting a lot of compute, or in fact, really simply, and just gone, here's the germline, change the residue to that. In case you're getting excited and thinking, well, maybe ESM2 is good at this. No, ESM2 is just predicting random residues because it doesn't know as much about antibodies. Interestingly, it still puts germline in almost 50% of the time. So it's a very powerful driver, this. So why is this such a problem? Well, the why it happens is quite easy. This is roughly the data in OAS in that pie chart. And most of the data we have comes from what are called naive B cells or unsorted B cells. And those tend to be ones where mutations haven't happened. Okay, so they're just germline. So you can see that in the pictures on the graphs on the right-hand side, the number of non-germline you have in there. And they basically have 0. Yep. And then we have a very small amount of data, which are what are called memory B cells. And these are the B cells where you've had an immune reaction to something and it's stored and it binds to something specifically. And you can see already, those are the green ones, we have quite a lot more non-germline mutations within them. But the thing to look at is obviously the therapeutics, the things we're aiming for, have even more. So if we are building language models that are basically a very expensive way of just recording a set of genes we already have in our body, we're probably not going to be able to make good therapeutic predictions from them. So that means that these models are skewed towards germline. They're skewed towards kind of the center of the distribution. And that might be potentially useful if what you want to do is humanize your antibody, because the germline's clearly human. It might be good if you want to stabilize it, because those are probably pretty good mutations because they're really kind of what we look like. But if I want to improve binding, it's not going to work. It's going to do the opposite. It's driving me towards, if you like, what I would call the naive repertoire, the stuff that doesn't bind specifically. So can you build a language model that will do that, given the shape of the data? I'm about to show you two really ugly tables in a row. I apologize for this ahead. Ugly table 1. This is really to show you kind of development of a model, because I often find people just go and then bang, we did a magic thing. Well, actually, as you all know, when you're building a model, you go through many, many iterations to get there. So from the purple line is our iterations, our attempts to build a better and better version of an antibody model. And we, first of all, changed our architecture. We went to an ESM architecture. And the thing that really makes the difference is below that blue line there, something called focal loss. Now, this is mathematically really well known, but hasn't been used in language models. And the reason it hasn't been picked up is it's very obvious. If you want a language model that's really good at writing a language, let's say the English language, you train it in all of the English language, what it wants it to do is use common words. So if it's writing a sentence that is, Charlotte has a pet, her pet is a, you want it to say dog or cat then. You don't want it to say shark or camel, because those are possible but highly unlikely. What focal loss does is it concentrates on the unusual events within the language you give it and makes it more likely to predict those, because what it does is it penalizes it for getting things wrong that are highly unusual in the data. Does it work? Well, what we're looking at here is a table of perplexity. I'm not going to go through exactly what that is, but it spans from 1, which would be a perfect prediction, to positive infinity, which would be you just can't get it right at all, which is sort of impossible to imagine when we only have 20 tokens here. What I find amusing is many of these things are worse than random prediction, which of course would be 20 in perplexity because they only have 20 amino acids. And what we've done is something that people didn't normally do. We separated out making the predictions for germline residues and non-germline residues. And what you can see is that as we move to our final model, ABLANG2, we're starting to get kind of better at getting the non-germline residues without destroying our ability to predict germline. So we can still get germline pretty much as well as we could before, but we're starting to get these non-germline residues coming in. The important thing to remember here, though, of course, is that one non-germline is not kind of the correct answer. That position might be possible to be 5 or 6 different residues. I just don't know that. I'm only comparing it to one sequence. So the last thing we did was we created sets, because we could get them from the data, where we had positions where we knew that this residue was non-germline, and we had multiple different residues had been seen at that position, and saw if the probabilities also agreed there. And we see the same thing. We see this improvement where we're just about starting to be able to make what I would call non-germline predictions in a sensible way. I think this comes with that little health warning. Language models are learning from a data set where most residues are germline. They're always the same. And you have to remember this is true for general proteins as well. If what you want is the rare event, language models are never going to give it to you because they're trained to give you the common event. And we're starting to be able to think of ways where we can actually use these models to push us towards the types of mutations we might want for those rare events. So I'm now going to jump to another property, which is humanization. So as I said, if you want an antibody to be effective, you want it to be human. You need it to be safe and human. About 50% of antibody therapeutics, and this is still true now as they come through, are derived from non-human sources. So we want a way that we can make these antibodies human. And to do this, we once again use the data from OAS. So I'm not going to train on human versus non-human in the sense of knowing this from experimental data. I'm going to just train it from the antibody sequences I can see. So I'm going to actually train 3 different CNNs, which are trained with this is what human looks like, this is what not human looks like, out of the data that we have in OAS. And the other thing is that we pair these sequences. So some of the data is only heavy chains on its own, some is light, and some is paired sequences with both chains together. This is one of those beautiful tables where you can just go, does my method work? Yes, it does. Because it is almost perfect. So you can see the precision recall under the area under the curve precision recall. If that was 1, it's perfect prediction. Yep. And this is for all of the different gene types that are making up the human antibodies. And basically, it gets it right. The problem almost looks too easy. You can actually see that some of the other methods can do slightly better, but we do just as well if we do it in a comparable sense, because we're trying to go as far as possible with the data that we can go. So yeah, you can do that. But that's not particularly useful, because that's just like, give me something, and I go, yeah, that looks human. what if I do if it isn't human? Well, thank you very much. It's not human. Great. Now I can't use it as a drug. So the next question we asked, well, is it actually relating to the experimental data? So this model has never seen any of the experimental data, doesn't know anything about what this is. So these are data on what are called ADAs, anti-drug antibodies. So these are things that have actually been given to humans, and this is the percentage of humans that actually had an immune reaction to it. That's the way of thinking about this. And so the data I've used is not related to this in any way. We just said, can it predict if you'll get an antibody drug action like this? And you can see it can. So we classify things, if we say that's really, really human, so on the right-hand side, actually it's very unlikely it will raise ADAs in anybody. If we say it's not human, oh, it might well raise some ADAs in people. And this is this is very useful and already, so now I'm starting to say, all right, I can now just say, not just I think this is human, I think this is safe, I think this is not safe. Not perfectly, but it's a really good start. But what you really want to be able to do is, can I actually move the sequence from being not human to human? So once again, I haven't trained the model to do this. I'm literally going to use the probabilities that come out of it. So the test we used here was, we've got a list of 25 therapeutic antibodies where people have actually published the precursor. So we know the humanized sequence that people experimentally made that is given as a drug, so that's my purple line up there, but we also know the yellow sequence that they started with, which was a non-human sequence. So we're going to do experimental humanization, well, that's been done, and we're going to compare our computational humanization to that. And that's what the table at the bottom is showing. It's the overlap between what the computer says and what the experiment says. And we've got 3 other computational humanization methods in the table there just for comparison. So I think, to be fair to those other methods, I haven't shown you the comparisons for the other stuff. Most of them, it varies a bit, are about as good at telling you whether something's human or not. So my lovely table with 1s in it. It varies a bit as well, but most of them are around about the same at telling you whether it's going to raise ADAs. So similar to this point. What we have here is, you can see that our overlap running our HUMATCH one is much greater with that experimental methodology. So what people know will work than any of the others. It's also giving a much more similar number of mutations in what it's tending to do. So we can't definitively show that we have a perfect method here, but we can show that it seems to be doing something sensible. And we think there are 2 reasons why there is a difference between our method and everyone else's. The first one is, if you remember back when I was talking about the CNNs, we humanized both chains at the same time, the VH and the VL. We had that paired model as part of what we were doing. Nobody else does. Everybody else has completely separated models. So you could humanize the VH, but then it might not work with a VL because you haven't humanized them together. They might be non-compatible in various different ways. And the second part of this is, and if this is once again going back to the beautiful table with all the 1s in, you saw that we did every V gene separately. None of the other models does that either. What that means, and I'll show you on the next slide, is that they're not actually targeting, if you like, a natural gene when they humanize. They can target a sort of mishmash between 2 genes, which doesn't exist. We have genes, and we build from those to make something that is human. It doesn't mean it wouldn't fold as an antibody, but it does make it much less likely to be human. So if you look at this image here, these are the kind of precursors and the sort of genes they fit in. And of course, they don't all fit into human genes. The right answers are the black squares. Yeah. So most of the precursors don't look like a human gene because they're not human. Then if you look at what happens with the other methods, they're very frequently not turning it into, in inverted commas, the correct human gene. Their probabilities are sort of spread across multiple genes or are the wrong gene. And if you go to HUMATCH, of course, it heads directly to a single gene because it is trained to do so. So we think that offers a second part of the advantage here. So humanization, and it kind of plays back to what I was talking about with the language model. The issue here is that it's able to kind of accurately evaluate whether an antibody is human or not. But the trick here is thinking about what's actually happening in the biology. The same with the language model. The trick was understanding that, of course, everything's going to revert to germline because that's what it's seen all the time. Here it is, once again, the antibody is a paired protein. It has 2 chains. So understanding how those 2 operate together is important in how you use the data and how you build your models for humanization. So now I'm going to go to the subject that everybody must be very happy and excited about at the moment, predicting the structure. So predicting the structure of proteins. And we wrote this software, published it last year, APBJC 2, and it's about predicting the structure of antibodies. And it has a lot of the components that are inside AlphaFold in order to make it work. And like AlphaFold, it's not a pure machine learning method. It actually finishes with some physics to make sure that we end up with a decent structure. But why did we build it? I mean, we were actually building it when AlphaFold 2 still wasn't out, but AlphaFold 2 exists. So what is the purpose of having this methodology? Well, the first thing to show you is it works. So that's the table at the top there. Those are the RMSDs for the various regions. The lower the number, the better. And, we'd say APBJC 2 is, I would say, APBJC 2 and AlphaFold approximately work the same. You'll see more bold numbers in my row than AlphaFold's, but I wouldn't take that as we're better. I'd take that those 2 work around about the same, okay? But AlphaFold Multimer, even if I optimize it and don't run it as well as it should be run, so actually its results are slightly worse than this, still going to take you 20, 30 minutes on a really good GPU. Now, that's fine if you want to predict one structure. That's also fine if you're DeepMind and have infinite compute. It's not fine if you're me and you have millions of antibody sequences and non-infinite compute. So the real thing about APBJC 2 is we've actually got it a bit faster than this now, but we can run it on a GPU in 5 seconds, which suddenly means I can predict the structures of a few million antibodies. And I can do lots of things with structure I couldn't dream of because I have structures of all of the antibodies that are in my sequence database. And I'm going to now show you a few of the things we can do because we can do that level of structure prediction. The first of these is the therapeutic antibody profiler. So this is about that developability question. Antibodies don't just need to bind. They need to be useful as a drug. They need to be able to be stored. They need to be able to be made. And back in 2019, we developed TAP, and we went for a different approach. Those of you who are chemists in the room have probably heard of something called Lipinski's Rule of 5. Yeah? If you haven't, it doesn't matter, but this is sort of based on the principles of that, which is what makes a good drug? Well, I've got lots of drugs over there. What are the properties of those drugs? My drug should look a bit like them. It's as simple as that. So instead of trying to correlate with experimental data, of which there is very little for most of these developability properties, we said, we've got a big set of clinical stage therapeutics. What makes them kind of a description of them? The good thing about this is it's not dependent on an assay. It's not dependent on having huge amounts of data, and it's totally interpretable. The bad thing is I don't have a really good list of what failed. So I only have a positive distribution here, which means I'm always sort of guessing where the edges of this might be, what you can actually do. So what are the 5 developability guidelines that we built in TAP? There are a set of really obvious friendly things. So turns out total CDR length is really important. The longer your CDRs, the more likely it is to be polyspecific, the more likely it is to aggregate, those kind of things. The amount of hydrophobicity on the surface, that, once again, aggregation, viscosity, you can see that. And then you've got positive charge and negative charge. Turns out these are very highly related to expression. So if you have too much positive or negative charge on the surface of your antibody, you will tend to have issues with expression. And then there is the charge between the 2 domains. So you've got your heavy and your light, and if they're not well balanced, you can also have issues, particularly with things like viscosity. And we implement this in an incredibly simple way. We build models of all the clinical stage therapeutics, we do a distribution of these measures, and we amber flag something if it's within 5% of the edge of the distribution, and we red flag it if it sits outside it. So that doesn't mean it's bad. But if you've managed to create a therapeutic which has way more surface hydrophobicity than anything that's ever been seen before, my suggestion would be not your best choice. Try and reduce that because it's likely to lead to problems. So the first part of this was we did an update. So the obvious things, we've got a lot more data to update with. So we've got a lot more clinical stage therapeutics now. We've got a lot more natural data to compare those structures with. So that's good. We can compare the background. And we also have this improved ability to model, which we looked at. The only thing that really changed as we did this, they all moved a little bit, yeah. But the biggest movement was in the patches of surface hydrophobicity. It tightened. So the distribution actually tightened a bit, which is unusual because we put more data in and it's got tighter. And actually, this relates to something that's quite well known. If you look at models, and as modeling has improved and look at crystal structures of proteins have much smaller patches of surface hydrophobicity than the models that have been built of them. And as your models improve, that amount of surface hydrophobicity, the patches of it, goes down. I don't completely know the reason for that, but you can calculate it and show it. So actually, this was a sort of confirmatory thing about what we expected to see. So that classification, once again, I'm kind of back where I was. I can now tell you, oh, that was bad, that's good. Can we do more than that? Can we use this to help suggest how you would make a therapeutic better? Can TAP predict what we should be doing? And I'm going to use light chains as an example here. So light chains come in two varieties, a kappa chain and a lambda chain. Back in 2019, only about 20 of the therapeutics we had were lambda, and we couldn't say a lot about what that meant. We got asked a lot of reviewers' questions, and we went, we've got 20 examples. I am not going to say what I think is going on. We now have 88. That's still not a huge number, but it's quite a lot more. So the first thing you can see, if I look on the right-hand side there, is that there aren't enough of them. So 13% of the therapeutics are lambdas, about 35% of your antibodies are lambda. So we're not using them as therapeutics. This bias might come about just by something very obvious, which is mice, where a lot of our antibodies are made from before we humanize them, actually don't have very many lambdas at all. So it might just be, we don't make lambdas because we're getting them from a source that doesn't have lambdas. But does the bias matter? I mean, you know, we're just missing out on some of this. It turns out it does. So there's been a lot of papers, particularly actually over this year, so called, the phrase they use is light chain coherence. What that really means is that specific light chains are needed for binding to specific epitopes. So if we miss out on a set of light chains, so if we don't use lambda, we will not be able to bind to some of the targets we are interested in. So can TAP help unlock lambdas for use as therapeutics? I'm just going to look at patches of surface hydrophobicity, but you could look at all the properties. This is just to keep it simple. So if I look at natural antibodies on the left, you can see immediately why we might be avoiding lambdas, because they're the purple distribution and their surface tends to be quite a lot more hydrophobic. So they're moved to the right compared to the kappa. You can see that both kappa and lambda antibodies, when they're made into therapeutics, they try and move their distribution kind of back less hydrophobicity than the natural set. So they're going, if I want to be a therapeutic, I want to be less hydrophobic than the natural set. But it's obviously getting much harder for the lambda antibodies because I've got further to get back to get into a sensible area to be able to do this. So they do have an intrinsic property that's going to make it a lot harder for them just randomly to be a good therapeutic. So can we do anything about this? Well, we looked at the obvious things. Are there any differences between the heavy chains paired? So is it related to that? Is that why we see these patches? Turns out it's not. But the cool part about this is that the positions that are driving that hydrophobicity are not in the binding site. And if they're not in the binding site, then maybe I could just change them and keep everything else, and then I will be able to use the lambda antibodies, use their lambda binding sites, but not have to worry about these issues around hydrophobicity. And to give you an idea about that, you can even go into the different lambda antibodies here, and you can see the number of flags they have. So we can see that some lambda antibodies are much, much more developable than others. So you could say I could focus on those types of lambdas because already naturally they will be much safer in terms of the amount that have green or red flags. So you can already do that. But you can also look, if I look at the right-hand side of this slide, at the exact positions that mean one lambda gene is safer than another. So you now not only know that this is unlikely to flag, you also know that I could make one mutation that is probably safe and human because it's occurring in another gene, and turn another gene family into being safe and keeping it human. So you have a very kind of sort of structured way to make your decisions about building an antibody, changing the residues that will allow you to create developable antibodies. The last thing that we did with TAP is something that a lot of people had sort of talked about and put some work around, which was when I do the guidelines, I take this static model of an antibody and I judge whether it has its surface hydrophobicity, for example. But of course, we all know that proteins aren't completely static. And if they're moving, maybe that reveals a massive patch of hydrophobicity, and so, of course, it's no longer developable. So this would be bad. And what people have done is run kind of molecular dynamics simulations and said, okay, does it show these patches during the simulation? The issue for me, once again, goes back to that speed thing. If I want to run these kinds of simulations, an MD simulation, even 200 nanoseconds of it, takes quite a lot of time, and I can't do that for millions of things. So we wondered if we could impersonate that in other ways. And what we actually did was just do repeat APBJC 2 modeling. We built 6 models. I'm still never quite sure why it was 6. I have asked this question a few times. But it turns out that that is a really good proxy for running the MD. It gives you just enough wiggle of what's happening to give you the same results as you would get from running the MD simulations in terms of whether this is developable or not. So I'm going to go on to talk a little bit more about this concept of flexibility. We are now in a world, and it is a very fun world, where mostly we can accurately predict, or accurately enough, they're not perfect yet, a single static protein structure. The problem is that proteins move. They have more than one conformation, and that flexibility can often be really fundamental to their function, and antibodies are no different from anything else. But flexibility prediction is really hard, and it's hard for a really obvious reason. There's not very much experimental data on flexibility, actually. We sort of know it happens, but we don't have a massive corpus of data to train a model from or think about. So we decided to kind of simplify this problem as much as we could and ask the question, could we predict the flexibility of what are the 2 most flexible, we know this, CDRs of an antibody, which are called the H3 and the L3. But even if I'm only doing that, if I look at antibodies, I still don't have very much data. So I'm going to do the kind of standard trick here, which is there another data source where I can get a lot more data that's roughly the same, and then see if that will predict for what I want to do. So what we did was we collected all of the loop structures between anti-parallel beta strands that are available in the PDB. So the CDRs on an antibody are between anti-parallel beta strands, so we collected all of these. And then we separated out specifically those from antibodies and TCRs. We just did that from SABDAB and our TCR database. We said 2 things were 1, conformation if they were within 1.25 angstroms. Doesn't really matter, pick your own cutoff, but that's just what we're using here. We called something flexible if we'd seen it in multiple conformations. So that was easy. I've seen it in more than one conformation, it must be flexible. Much harder to say if something's rigid, because you could just take everything, but of course loads of those might be flexible. I've only observed them once. So we gave ourselves quite a strict cutoff. We said the loop had to be seen in a single conformation in at least 5 separate PDB structures. That still doesn't mean they're rigid, but it gives me a much higher chance that they are. So I will have rigid loops and flexible loops. And I've got the numbers that we were using over on the right. We used equivariant graph neural networks to do the prediction here. And we used the input was the loop itself plus all the residues within 10 angstroms of the loop. So you've got the loop and its context is how you're doing the prediction. The node features are just the amino acids and whether it's in the loop or in the context. And then the edges are is it a covalent bond? So you're basically telling it the protein structure as you go, and the C alpha distance encoded between 0 and 10 angstroms. And this is the results of all of that. So this is testing it on the antibody CDRs here. So CDRH3 and CDRL3. And those are the number of examples in the test. And there is nothing in the data that looks anything like these, just to be clear. And the first thing is, of course, the random baseline isn't that bad at doing this because of the disbalance you have in the data. Things that we wanted to check was that we weren't just predicting if a loop was solvent exposed and how long it was, because the more solvent exposed something is, the more likely it is to be flexible. The longer it is, the more likely it is to be flexible. And so those are those baselines, and we combined them to show that we can actually do quite a lot better than that. And then we compare to other methods for doing this. So AlphaFold, PL-DDT score, or MSA subsampling to make lots of conformations of AlphaFold, which people have used to do this flexibility prediction. And then you've got our results at the bottom. And we're pretty happy with them. It's not a perfect predictor yet, but it is working. And perhaps the most important thing here is if we do it on models, the results are not getting worse. And that's something we wanted to build in the way we did this, because it's useful if I can do it on a crystal structure. It's way, way more useful if I can do it on a model. So now I'm going to come to my last kind of story of the talk. And this is one of those questions that I think people haven't really sort of got to grips with. We sort of play around the edges of it a lot. Can machine learning models actually extrapolate? They're a data collection thing. They take loads of data. As far as I can tell, they're fantastically good at interpolating. But in some regions, particularly in the worlds that we work in, we might want them to extrapolate. There's some work that's been done with AlphaFold to try and work out if they build new folds, and definitely it has built some folds we haven't seen before. But in order to build those, it's gone alpha helix, loop, and if you look at each piece of structure, each one of those kind of defined segments is something I can go and find again. So at what level can it extrapolate? At the level of an individual residue, at the level of a loop? So we decided to test this, and fortunately in antibodies, we have a beautiful way of being able to test this. We can create a really strong test. If I look at the CDRs apart from H3, so 5 of the CDRs have what are known as defined shapes, which are called the canonical classes. So they fall into very specific shapes. It's one of the reasons they're easy to predict. So we nearly always see them in one of these shapes. There's quite a lot of these shapes, but that's what we observe. So I can ask, do I ever predict a novel canonical form? Something that doesn't look like any of the known structures. So the test, sort of straightforward. I'm going to take observed antibody space. I took about 1.5 million non-redundant paired sequences, built models of them, bang. I structurally classified those, and I'm going to show you lots of the pictures that look like the things at the bottom. They're pictorial representations, they're T's and E's, but the numbers I talk about are actual clusterings. I'm just showing you these as pictures because it's easier to do. And I'm going to compare what I get to this Ronald Dumbrack's PIG classify, which is, this is what the canonical forms look like. So do I ever get anything that isn't a canonical form that I already have in SABDAB? So the first thing is, if I just do this, and this is just one example. So on the left-hand side is what you get from SABDAB. Yep. On the right-hand side is what you get if you like out of the model. So these are my 1.5 million models. And you can see I basically get the canonical forms back again. And this is kind of not bad, because obviously most of the time that's probably right. And you're getting these structures back and it all makes sense. So do we get new structures? Well, I would say sort of no, but I can get you a little bit excited about things we do see. So the first thing we see is we get new clusters in the sense that suddenly there is a cluster where there used to only be one data point. And that's really because I've given it 1.5 million structures rather than 6,000. So instead of only having a few examples in that area, so nobody called it a canonical form, I now have several thousand. So it goes, oh, look, canonical form shape. So it's not predicted something new, it's just kind of added a lot of data to that point. You can also help redefine the experimental data. So in this case, the blue and green loops there were considered one canonical form. And once again, I think that's to do with lack of data. But once you pour loads more data in, you're able to split them out and show that there are actually two shapes in operation there. So I would argue, once again, not novel, but helpful in defining the space. And then there was the bit where we did get a bit excited, which was we started to see, we thought, wow, new canonical form. It turned out that that shape was available in something that was only one length different. So it was one amino acid different in length. So what it was actually doing was, if you like, extrapolating from one length to another. It was saying, if I can see this in length 7, and the sequence matches and everything else matches, I can build a very similar shape in length 8. So that's kind of cool, because that's a real kind of step. And we know that actually happens with antibodies as well, because there is length independence in the canonical classes. So the model has picked that up. It really doesn't like me. I'm waiting to be told if I'm having an emergency again.
It's just a heavy rain alert. So
it's telling me it's raining.
No,
So maybe there aren't new canonical classes to find. That could be the other answer to this question. Maybe we've already got them all, and that's why I can't make it extrapolate. So let's make the question really real. So what I'm going to do here is create what I'm going to call a starved model. I'm going to take out an entire canonical class and then go, can you predict it? Because I know it exists. I know there are sequences that should have it. Can you do this? So we've got what SABDAB looks like on the left-hand side. We've got the original A-body builder 2 in the middle, and then the starved model on the right. And let's look at what happens at the top. So what we took out was that purple canonical class. So you can see SABDAB and A-body builder 2, they agree, that's what happens. You can see the canonical classes. In the starved model, and this seems to be what happens every time, it doesn't get it right. So you can now see the purple dots are not in the right place. But it also doesn't put them in another canonical class. So it doesn't say, this is like everything else. It goes, this isn't like everything else, but actually I don't know where it goes. And that's a pretty good description of what happens. You can see a similar pattern if you look at the pictures at the bottom there, where we remove the green canonical class, and it predicts them all together, but it puts them in the top quadrant rather than in that bottom quadrant. And this seems to be a pattern. We did this with several examples to try and show this. So the final question is, well, okay, maybe it can't extrapolate. So do I have to be miserable because I'm never going to be able to build a great model if this keeps happening? It's going to recapitulate my data. It's incredibly powerful. It's really useful, but and actually, it's not quite as bad as all of that. And the reason it's not so bad is really what's happening in this picture here. So what we've done here is starve the model again. And what I mean by that is given it no data. And then we've very slowly added in a tiny drop of data at each point in time. Yeah. And what you see is with a very, very small amount of data, so even if I only add in a few data points, so the 0.16%, already it starts to go bang, it finds the right canonical form. So there is massive hope here that these models, despite the fact that they're data hungry, as much data as possible is brilliant, that they are incredibly good, even with only tiny amounts of data that relate to these conformations, at correctly picking up these things. So if we target how we develop data, we have huge power available to us for making these things go better. So just to finish up, I hope I've vaguely convinced you that we can already predict many, many useful properties of antibodies, and you can plug lots of these things together to create something that might be useful. I hope I've also convinced you, because it's basically a really important statement I feel I have to make in every talk I ever give, real care must be taken in assessing the predictive ability of these models. It's very easy to overestimate our ability to do clever things. I think, and it's sort of true in everything I've been trying to do, making the best possible use of the data is absolutely key in all of this. So I should finish just by saying thank you to all the people who actually did the work. So that is my current research group on the right, and then on the left-hand side, a year and a half ago now, we had an invite back to all of the members of my group over multiple years. And as always, this work is built across all of those years with all of these people being involved. And finally, I should say a massive thank you to all of the organizations across the bottom of this slide. because they literally give me money to allow me to do my favorite thing. Thank you very much.
Excellent. Thank you for a great talk, Charlotte. So we have some time now for questions. So if you have questions, please do come down to the microphone at the front. And to get us started, I'd like to ask you some questions. So I suppose one of the things that seems a sort of a problem in my work is overtraining. So particularly here, it seems like you're trying to overtrain your models. They work better if you give them everything. And is that a problem?
It operates in two different ways, actually. So in some of the cases, yes. I would say the overtraining is literally what we're trying to do. We're almost trying to overfit to the antibody data or force it into a corner there. In other cases, and actually the language models are the best case of this, so our generative models for generating antibody sequences, actually it's a real problem. You need to pull back quite hard. Otherwise you end up in this, I'm just going to predict germline, I'm just going to give you germline, I'm just going to... And one of the major issues with using machine learning for all of this is, of course, it's doesn't have a statistical underpinning. So we don't know when we've done this. We can only do this by observation. So I'm afraid my answer is you have to keep looking at what happened and go backwards and forwards again and again and again.
Yeah, always look at the data. Okay, yes, please.
Thank you, Charlotte. And hello. Okay. Hello.
Do you want to just come up and ask the question here while we're waiting?
Hello, mic test.
No, please. Yeah, come.
Okay.
Yeah.
Oh. Pretending to be Charlotte. I have a question for you relating to both what Alex said and your last minute, where you mentioned that a few points was enough. But I guess this is sort of well known that if you have samples that are very similar, you only need a few of them. However, in your experiments to do this, you are adding a little bit at a time. Whereas if you have started with a model that maybe in some of the cluster space, you have a big cluster already, then if you have a new cluster space with a few samples to use to observe this behavior.
So that's exactly how we did do it. We'd left all the other data in. So some of those canonical forms are completely dominant, like for some loops, 80% will fall into one shape. And yet we are still able to get the other shape by adding a tiny amount of data.
Okay, that's great.
So it is, I find it amazingly positive because like you, I thought, well, it will.
Yeah, because everyone has this myth that, the unbalanced classes make now bad.
And I think they can do, but I mean, this, to be honest, I think canonical form prediction is almost an easy extrapolation task. Which is a shame it still failed on it, but it's a good starting place to be able to understand whether we can do these things and what we need to do.
Great.
Thank you.
Thank you. Okay, so any more questions from the audience? Okay, so we do have a couple of, we do, excellent. Okay, fingers crossed, Shobha, that the microphone is now working.
No, sorry.
Charlotte, you're inviting us all to the stage.
It's way better that way.
What an incredibly exciting presentation. I mean, this is mind-blowing work. I wanted to just make a point that AlphaFold 3, which has just come out in May this year, seems to be adopting all the old technologies of template-based modeling. They have used MSAs, deep MSAs, and they have also used a whole bunch of PDBs as templates for their learning. So maybe you would like to see whether your observation of surface hydrophobicity could actually discriminate between a good model and a predicted model, which which comes out through one of these prediction systems. The other thing I wanted to say was that one of the driving forces of protein folding is burial of the hydrophobic regions. So that's what you're actually showing the world in your studies.
Thank you, Shobha.
I think, I mean, really, we're not trying to show that it is absolutely correct that burying the hydrophobicity is what is happening in a protein. It is just interesting to me that the structural prediction methods somehow don't quite know that. I think it's also to do with their prediction of side chains on the surface more than anything else. So they're placing the side chains, and with the surface, so it's not so much what they've put inside, it's the surface itself. They're putting side chains that are hydrophobic and choosing conformations that put them close to one another rather than pointing them away, which reduces the patchiness of the hydrophobicity.
And so are we missing glycosylation here? Does
Yes.
that play a role?
Yeah. There is no glycosylation in anybody's models because there's barely any structural data to make a really strong model around that. And it plays quite a big model in antibodies.
Okay, thank you. So we are just about at time. Yeah, okay, so come on up.
Yeah, definitely.
One last question.
First of all, thank you very much for your talk and for navigating the irony of a British researcher interrupted by rain alarms throughout the talk, so well done. I just wanted to ask that in computational biology, we often have to limit ourselves to what is possible in biology, right? What we're looking for or modeling should be seen in biology, perhaps. But maybe for you, this is not a limit that you have to put on yourself. How did you strike the balance there, actually?
So I think that's it is literally a balance, because if you're trying to make a therapeutic, I somehow do have to limit myself because I want it to be human.
Right.
If you're trying to design novel proteins, you don't have to limit yourself at all. So you can think about making antibodies that would make great kind of tool molecules, so starting points for things, where you can really muck around with this. So those predictions about, that ESM2 makes, for example, in the language models, I suspect are pretty interesting in terms of thinking about antibody structure, and people have used it to improve stability, say, of antibodies and other properties. So there's really exciting things you can imagine of non-natural antibodies that would be fantastic for lots of this. So it's sort of a game you can play here because there's such a nice scaffold. Yeah.
Excellent. Okay.